This image was taken after a charter fishing trip in 1957 in Key West, Florida. The image on the right was taken in the 1980s in the same location. The difference in fish sizes between these two time periods is staggering. This phenomenon of fish getting smaller over time is known as size truncation. Size truncation is the effect of large fish being systematically removed from the population, resulting in an average size that skews smaller and smaller over time. Size truncation negatively affects fish populations because it is the largest fish that produce the most and highest quality eggs. Take the coral trout, which can be found in Australia, as an example. A 60-centimeter female can produce over 8 times as many fish as a 40-centimeter female. Additionally, size truncation affects biodiversity through its effects on community stability. For example, removing large fish that eat sea urchins might allow sea urchin populations to expand out of control. It affects fish recruitment because a wider range of fish sizes reduces recruitment variability. It affects population genetics by removing fish that tend to mature later and grow faster. Size truncation can also affect economies and food security by reducing overall catch. Size truncation is widely attributed to overfishing. Although this is the case, there is still a lack of comprehensive data in California fisheries. This lack of knowledge is what motivated my capstone research. I aim to not only confirm fishing's effect on size truncation, but also determine if there might be other drivers and present a more comprehensive view by also analyzing environmental variables. My research focused on recreationally caught fish in the southern half of California, as depicted in this image. This region has a very sizable and active recreational fishing sector with a wide variety of fish species. All fishing data came from the publicly available California Recreational Fisheries Survey, or CERFS, which spans from 2004 to present. CERFS data includes fish lengths, fishing effort, and landings data. Length data is collected by California Department of Fish and Wildlife samplers. Often they measure fish as fishermen bring them ashore. In my study, effort is characterized by total angler trips for commercial passenger fishing vessels and private vessels. Landings are characterized by total mortality per time period. Effort is different from landings in that effort indicates how hard people are actually trying to catch the fish, and landings indicates the amount of fish that were actually caught. There were 2 environmental variables used in this project: temperature and an upwelling index. The upwelling index I used is called BEAUTY, which stands for the Biologically Effective Upwelling Transport Index. This is a relatively new upwelling index that measures near-coast nitrate transport to the surface layer. I used BEAUTY because it may be more relevant to biological processes than other upwelling indices. The main results of my project come from the use of a statistical analysis tool called Convergent cross-mapping, or CCM. CCM is unique for a few reasons. It works in complex, nonlinear systems, which most ecological systems are. It's useful for showing causation, unlike traditional statistical methods. And causation can be detected even when correlation is not present. The way that it works is, if fish does indeed cause fish size to shrink, then fishing effort data should leave information in fish size data. Because of this, you should be able to work in reverse and predict historical fishing values with today's size data. So, if fishing yesterday causes size today, then size today will predict fishing yesterday. This is an example of the length data for grass rockfish, which is one of the 3 species I found to show size truncation during this time period. Every dot that you see is a single fish that was caught. The x-axis shows time and the y-axis shows fish length. To put this data in a format that is usable for the statistical analysis in this study, I selected the top n number of the largest fish per quarter, average them, and then calculate the 4-quarter moving average. To figure out the n number, I use simplex projection to figure out which number of fish displays the most coherent signal. This is done for the big fish and the small fish. Here's what the big fish time series of grass rockfish looks like after I perform these transformations. As you can see, there's a clear negative trend in the biggest fish of this species in the southern half of California. I applied the method described in the previous slides to 15 species in the southern half of California. I then performed a correlation analysis to determine which species showed a negative trend over time. 3 of the 15 species displayed a significant negative trend over time: grass rockfish, square spot rockfish, and speckled rockfish. This provides empirical evidence that size truncation is indeed happening to fish species in Southern California. These are the CCM results for grass rockfish. Above each bar, the row is displayed. This value tells how well fish size could predict past values of the driving variable. This goes back to the concept of CCM predicting backwards. The row value contains linear effects, i.e. correlation, and nonlinear effects. Identifying the nonlinear effects provides more confidence in the fact that the driving variable is indeed a driving variable and not simply a correlated variable. In order to remove the signal from the linear effects, I subtract out the correlation between each variable. This gives us the height of the bar, or the y-axis, which I call CCM minus correlation. On the left are the results for the big fish, and on the right are the results for the small fish. The x-axis is showing the driving variables. I've crossed out results that are not statistically significant. One interesting outcome here is that temperature displays a stronger nonlinear effect on small fish than on big fish. It was actually expected that temperature would have a larger effect on small fish than big fish, what you're seeing here. This supports hypotheses that smaller fish are more influenced by environmental variables than bigger fish. Secondly, effort shows a much stronger nonlinear effect on big fish than on small fish, which showed no nonlinear effect and very minimal correlation. This was another expected result and helps to support the main hypothesis of this study that fishing is a driver of size truncation. To add further support to these two hypotheses, all 3 species displayed these two patterns that I just showed. Grass rockfish was unique from the other species in the fact that temperature displayed the largest effect on big fish compared to fishing variables. For the other 2 species, fishing variables displayed the strongest effect. A third interesting result is seen by going back to the correlation plots displayed earlier. In 2014 and 2015, water temperatures off the coast of California were affected by an unusual warming event known as the blob. Here I have highlighted this time period during the blob in pink. All 3 species displayed a drop in size during this period. From this, it was not surprising that temperature appeared as a significant driver of large fish for all 3 species in the CCM results. It should be noted, though, exactly how temperature is influencing size was not uncovered during this study. It could be due to temperature's effect on growth rates, or it could be due to temperature affecting the catchability of the fish, since all of the length data here comes from fishery-dependent sources. This would need to be further investigated. Despite not understanding the exact mechanism, this study provides evidence that temperature may have a major effect on large fish size. This highlights the need to further study the effects of climate change on fish populations and to take climate change into account in fisheries management. Additionally, this research adds to existing evidence that fishing does induce size truncation. This is significant because it amplifies the need to employ management methods that take into account the importance of big fish. This is especially important since most current fishing regulations actually encourage size truncation by only setting minimum size limits. With these findings, it is clear that an adaptive and climate-aware approach to fisheries management is crucial to protect both the health of our marine ecosystems and the sustainability of our fisheries. I'd like to give special thanks to my capstone committee, Lyle Belquist, a senior fisheries scientist at the Nature Conservancy, George Sugihara, a Scripps professor and researcher who developed CCM, Nick Wegner, a fisheries biologist with NOAA, Tom Mason, a fisheries policy expert who works for the California Department of Fish and Wildlife, and Eric Sabursky, who is my PhD mentor. Thank you. Any questions? Chris.
I won't yell. I'm curious if one possible result of your work down the line might be to induce size limits for catch of some of these size truncated species. So you can only catch a fish up to this size and not beyond. Is that something that might be plausible given your findings?
For sure. That is actually one of the main methods that you would use to counteract this effect is to set a maximum size limit. Just setting a simple maximum size limit would be the easiest way. You can also set harvest slots to where at certain periods in time you can catch big fish and certain periods of time you're not allowed to catch big fish. They actually do in the West Coast use maximum sizes on just a very few amount of species though.
I've got a question. Do you think, Rob, there's a specific way to manage fisheries that might mitigate the issue of size truncation?
Sorry, can you ask it again?
Yeah. Is there a specific way to manage fisheries that might mitigate the issue of size truncation?
For sure. That kind of goes back to Kristen's question, to where just the simplest way would be to put in place maximum sizes for fish, not just minimum sizes. But then you can also use harvest slots where at different times you're allowed to catch big fish, and then at different times you're not allowed to catch the big fish.
Thank you. That was really interesting. I noticed in the data that the size went through this really periodic decrease and increase, and it seemed consistent through all three species. Do you have any thoughts about that? Is that random, or do you think there's something going on there?
For sure. The raw data definitely had a lot of seasonality in it, and the seasonality was likely due to sampling, the way sampling's performed, and also just natural patterns of fish. All the transformations that I applied to the data were intended to mitigate all of those effects. So the 4-quarter moving average took the average over the entire year of all the biggest fish, which was intended to reduce the seasonality. But as you can see, it was pretty difficult to completely get rid of the seasonality for sure. Thank you.
Does the age of the fish have anything to do with these numbers and the statistics?
Yes. So age and size are very closely correlated. But the reason that I'm using size data here is because there's a lot of size data, and measuring fish age is a lot more difficult than just measuring size of fish. So that's one of the reasons why this study focused on size.